Hi, everyone. Welcome back to Transform. I hope everyone's been having an awesome first day of tutorials. Thanks again to Studio X for sponsoring Transform conference. So I'm very happy to introduce Michael Pyrcz. He's going to be giving us this tutorial for this next 2-hour period. You'll find information and links in the YouTube description below for today's tutorial. And if you have any questions or want to start any discussions, you can ask in the Software Underground Slack channel, T21 Monday Geostatistics. So I'm very happy to introduce Michael Pyrcz from University of Texas, Austin. He is an associate professor working on spatial data analytics, geostatistics, and machine learning. So I will hand it over to him to get us started.
Ashley, thank you very much for the introduction. I do appreciate that. Let me go ahead and share my screen. I should be sharing my screen right now, and I'll put some slides up just to get us started. Don't worry, it won't all be PowerPoint based. I will have a lot of code to show. Let's go ahead and start walking through this. All right, you can see my slides. As mentioned before, I will be monitoring the Slack channel. If there's questions, go ahead, jump in. I love interactivity, and I love the opportunity to discuss with people. What I'm going to do with this basic introduction right here is going to be very quick, just a short introduction of myself. Who am I? What am I doing? What am I interested in? And why am I here? Introduction to GeostatsPy, the open source package for geostatistics. Talk about the plan, getting set up, help you all so you can follow along. Or if you can't, you can always just, if you don't set up locally, I will talk enough, I will show enough on my side that you should be able to get quite a bit by watching and asking questions, interacting. Have a call to action and then the very quick schedule. Welcome everyone. Thank you very much. Matt, Brendan, Irene, Ashley, everybody who's participating on the Software Underground side to organize this event. I do advertise it to my students as one of the best events to attend to learn about computers and geoscience and new digital technology. So thank you very much to everyone who's organized this. The entire course, all of the content that I'm sharing here is and has been placed already on GitHub for you. If you go to my account, Geostats Guy, you go to GeostatsPy_course_2, you will get to a repository where I have all of the data sets. I have a bit of a description, introduction here, explanation about what you need to do to get set up to be able to work along. All of the data sets that I will be using are available there. The lecture slides that I will cover in PDF are all available, and all of the workflows that I will show. If you want to have the exact same setup as I do, I put an environmental YAML file there so you're able to set up your local environment to mirror my environment and ensure that everything will run. The one thing you may run into is that you should be working with Python before 3.9 because of a reliance on Namba for acceleration. And that's all available to you on that repository. You'll see that. All right. I also want to mention my motivation here is really to promote the use of GeostatsPy package to enable spatial data analytics and geostatistics workflows in Python. It is based on the original geostatistical library, GSLib, which was just an amazing, powerful set of open source software that was given to the entire world along with a great handbook, GSLib, Geostatistical Software Library and User's Guide by Clayton Deutsch, my PhD advisor back in the day, and Andra Janelle from Stanford. This is an amazing software development that's very well tested and well used, well applied in Fortran, fast and efficient. And the idea was to make these tools freely available to our people in the Python community and the Python ecosystem. And I think that's a great opportunity. Who am I? I'm Michael Pyrcz. If you've never met me in person but seen my name and you're wondering how would you pronounce that, you can say just Pyrcz, and that would be fine. I am relatively new to academia. I have about 17 years of experience consulting, teaching, working in industry on subsurface statistical modeling, reservoir modeling, uncertainty, and so forth. I left industry to teach. I love what I'm doing as a professor. I like teaching. If you're from an institution, invite me. I'll come give a lecture, or I'll go teach. I do that all the time. I'm happy to do it. It's a lot of fun. And I did write a book. If I could now, if I was to rewrite the book, or maybe the third edition, I would rename it Spatial Data Analytics and Geostatistics for Subsurface Modeling. That's what I would do, because I feel much of what I share with you around geostatistics is spatial data analytics. All right. I'm also active on outreach and social media. All of my lectures are recorded on YouTube, on my YouTube channel. I'm the Geostats guy on Twitter, on YouTube, on GitHub, and I share a lot of resources to support working professionals, students all over the world. Okay, let's talk about GeostatPy. It was back in 2019, the spring, I was teaching for the first time a subsurface data analytics and geostatistics course, and I had a bunch of geoscientists and engineers. I wanted to run it like a semester-long simulation where I was the subsurface manager and everybody in the classroom were the geostats, the subsurface modelers. And I walked them through the entire, from data to estimation to simulation to uncertainty to decision-making workflow over the course of the entire semester. The class filled up very quickly. Everything looked great. I was excited to teach the class. And then what happened? That very first day of class, I tried to go ahead and get started. And what I found was that the resources I had available to me, GeoSlive and Fortran, was a non-starter. In fall 2017, I tried to use that. I lost half my students the very first 2 weeks because people got frustrated trying to work with Fortran. What I found also was I had done some previous work in some really cheap, not great wrappers that didn't work very well. And so what I realized was I needed to do something different. I needed to still use the geostatistical library, but I had to make it accessible in Python. Now, I want to recognize the fact there's GStat in R, Edzer Pebesma. They're very cool, very, very useful, but I found it somewhat impractical for the students beyond univariate simulation, and it was not currently under development. PyGeostats at the time was completely behind the consortium wall and was not available. So I tested a variety of packages, and what I found was that things were just breaking, things weren't working in time, and so I needed something robust just to get the job done. So I spent my weekends before the lectures, days before class, working on coding this up. GeostatsPy, how is it structured now, is broken up into two main modules, GeoSlive module and GeoStats module. GeoSlive module is really focused on a re-implementation of the basic visualization diagnostic type of algorithms, the import-export of Python and GeoSlive files, GeoSlive being in a GeoDAS format, and also wrappers. And these are not great. They're literally saving the parameter files, running the GeoSlive executables, and reading in the outputs. GeoStats module is the true re-implementation of the GeoSlive subroutines in Python. All of the building blocks are available there, and then re-implementation of most, I think I have full coverage of the two-dimensional approaches and partial coverage of three-dimensional modeling approaches. It provides GeoSlive-like data visualization, very easy to work with within the Python environment. It's a great bridge for new users, people who are used to the GeoSlive-like plots. It's recreating them under the hood just using matplotlib. It uses the GeoDAS ASCII format for files for ease of being able to work with those files. Lots of methodologies to be able to load and save and move across those with those files back to pandas, data frames, and ND arrays. It also provides these wrappers by which we're able to run executables from GeoSlive. Now, I have to say, I like doing that because the GeoSlive code is very well tested, it's very well established, it's very fast. And so at times in my workflows, I will run these, and they're as poor as they look. They really are just writing out the GeostatPy parameter files, accessing the operating system and running those executables. So it's not true integration across platforms, but I still think it can be useful. The re-implementation of all of the subroutines gives you all of the basic building blocks for working in spatial estimation and simulation, spatial covariance, geometric distances, rotations, Kriging solutions. All of this is implemented as very nice, small members that allow us, or functions that allow us to be able to build up the geostat methodologies. And then all of the approaches, declustering, which I'll show today, for Gaussian simulation, I'll show today, and all of the other types of geostatistical tools in GeostatPy standard library is available here in 2 dimensions. Okay, I want to acknowledge the contributors. I led a lot of the writing. I've written a lot of this code, but I do want to acknowledge graduate students Hong Kong Zhou, Wendy Liu, who have worked with me and helped to develop additional functionalities specifically around 3D. Anton did a great job with putting a bunch of good documentation and proving the compliance with PEP 8 and so forth. And Alex were providing some initial unit tests for continuous integration and so forth. So I would love to see this expand. Part of my motivation in talking right now is a hope for people to jump in on the open source. Co-authorship is cheap. Basically, contribute to it, send a pull request, and you'll be a co-author of the open source package for sure. What is good? We have a lot of good documentation and examples available to anyone in the world. And what is also really good, we have a lot of demonstrations, including interactive demonstrations that I will show you. It's all available on PyPy repository, and we have a lot of great examples available. In fact, if you want to do something geostatistical right now, I challenge you. You would be able to take an existing example, well-documented demonstration workflow and apply it to your problem. Change out the data file, make some modifications. You'd probably be able to start getting the job done pretty quickly. What needs work? Well, clearly there's an opportunity to improve doc strings, documentation. Every package has this, more documentations. Expanded spatial data analytics and spatial statistics. We've done things like semi-partial correlation coefficients, Ripley K functions, L functions, and true spatial statistics. I think it'd be good to have more of that available. That's not available readily, efficiently in other packages, of course. I think there's a lot that can be done on efficiency optimization. I mentioned that we have a reliance on Numba, and we do that for optimization, for speed up of the run, and support of full 3-dimensional workflows. I think that's essential. What's the plan? Let's go ahead and build from zero, and we will cover some fundamental ideas in geostatistics that are critical for spatial uncertainty modeling. We're going to build up on spatial data debiasing. Why? Because if you don't account for bias, if you do not mitigate for bias, your uncertainty model is wrong. Spatial uncertainty modeling by stochastic simulation. We'll talk about some principles and we'll cover how to do it in GeostatPy. And then we'll talk about how we summarize over uncertainty models using post-processing in GeostatPy. We'll do this all with 2-dimensional synthetic subsurface data sets. We'll do 2-dimensional displays for fast runs for something we can visualize very quickly. How are we going to do that in just 2 hours? Well, we'll rapidly cover the concepts with lecture slides, but we'll spend much of our time in code together. For those of you interested in deeper knowledge, my YouTube channel does have all of these topics and much, much more. The entire course on subsurface data analytics and geostatistics, and an entire subsurface geostatistical modeling course. So all of those are available to you. You can come back, go to the channel, check it out. They are linked to workflows in my GitHub account. You can actually run along with all of my workflows and learn this in greater detail. How are we going to do this? We got interactive demonstrations. I've recently kind of got a little bit addicted to the whole thing of ipywidgets. I just find it a lot of fun for teaching tools to be able to teach concepts like spatial continuity quantification through the Varigram model. And then I can immediately switch over to an interactive Python matplotlib ipywidgets display dashboard, and my students can immediately start to learn how to do it. You can customize it for maximum diagnostics and interpretability. What am I saying? The best way to learn is to play with the machine or the algorithm. And that's what I try to do with all this interactivity. We have walked through well-documented workflows. At times, I will open up a workflow. We're just going to walk through it together. I'll talk about it. If anybody has a comment on the questions or chat, do it on Slack and let's discuss. I really do like interactivity, but I'll show you workflows and we'll talk about them together. Well, the goal here is to really be able to showcase GeostatPy. I can't teach spatial data analytics. I can't do that in 2 hours. I wish I could. I can't. Check out my YouTube lectures for greater depth. Check out all my examples on GitHub, and you can gain greater understanding. Let's talk about the setup. You should be working with Anaconda on your laptop, Anaconda 3, to make sure you have Python. Now notice Python, the actual version of Python you have should be less than 3.9. That is because Numba is required, and last I checked, that is not up to date with the current newest version of Python. I can't rewrite all of GeostatPy to take account of that, specifically because I work 7 days a week already as a professor, but I can't really fix that problem on my end. Neither do I want to. I want to have Numba acceleration until there's a better option for reasonable runtimes. Install GeostatPy. You just do a pip install GeostatPy and away you go. You'll have that available for you. It's on the PyPy repository. It's version 0.0.19 and you're good to go. I would recommend working with Anaconda 3.8. If you want to have Python 3.8, that would work really well. And then just do the GeostatPy install and you're good to go. If you're new to that, it's very easy to make sure everything gets done in the right place, not any complexity around environments and so forth. If you are an expert, just stop listening now. Take a break, have a drink of water or something or coffee. But really, once you've installed Anaconda 3.8, what you can do is you can go to Anaconda Navigator, go to your base environment, hit the play button, select open a terminal and do the pip install GeostatPy run there. I know it's very simplistic. What I'm trying to do is just make sure that you install it in the right place. When you open up your Jupyter Notebooks, you're going to in fact have GeostatPy available. I do this with my students in my classes, and they tend to be able to run all of my examples without any issue. Call to action. What do we want to do? Well, contribute. Join in. It's open source. I would love to work with more people, work with my PhD students, work with, amongst yourselves. This is open source. It shouldn't just be me. Docs, optimization, coding standards. There's so much. You will see that there is no shortage of work to do. All right. Let's go ahead and let's jump into content. Okay. How are we doing? Any questions or comments while I do that? You're welcome to put them into Slack. The Slack channel is T21-MON, M-O-N, geostatistics. Go ahead and join in there anytime, make comments. I do welcome them. Let's talk about bias. Oh boy, this is an important topic. We got to cover this. What I said before, why for spatial uncertainty would we talk about bias? Because if you have bias in your model, your uncertainty model is wrong. And I don't see enough people in their subsurface spatial workflows using debiasing methodologies. So I do want to encourage that. Okay, good. I do appreciate that feedback. It's working with 3.9 in the meantime. So go ahead, if Numba is working with 3.9, go ahead and use Python 3.9. Maybe that was something temporarily I was running into, but go ahead, that's good to know. I appreciate that comment back. Bias, naive statistics from biased spatial data samples results in biased uncertainty models. How many times do you get to make a statement and use the term bias 3 times? That's a lot of fun. And we know that that's an issue. In fact, let me go a step further. Your sparsely sampled subsurface data sets are biased in their sampling. In general, that's the case. What's the problem? We have to work within an area of interest. And in fact, we have samples that are not sampled for representativity. Let me talk about that a little bit more. As mentioned, I do have a lot of lectures available on this. I have specifically a cell declustering lecture where I talk about spatial debiasing. I do have another lecture where I talk about a Python workflow for spatial debiasing, which I'll show. I have a walkthrough recorded already. And I have another one where I talk more fundamentally about the sources of spatial data bias. Let's cover just enough so we can move forward together. How do we decide where to sample subsurface data? Well, this is very interesting. It turns out that we collect data to answer questions, to minimize or to reduce uncertainties. How far does the contaminant plume extend? Well, we're going to sample the peripheries of the known location, map location of the contaminant. That's because that will be an important uncertainty for us to resolve as far as decision making. Where's the fault? We're going to drill based on a seismic interpretation to try to resolve the uncertainty in the fault. It's a sealing fault. That's important. Highest mineral grade, how far does the reservoir extend? Groundwater, whatever it is, we're drilling to reduce uncertainty. That's a good idea. We also drill or sample the subsurface to maximize value, maximize recovery of resources from the subsurface early in the project to pay off the cost of the project. That's a shorter payoff period. That's good news. These are the two ways that we determine to sample. Now let's go back and let's look at this. We got an area of interest. We have our samples. What are we doing? Our goal is to assess the overall quality of the rock. In fact, if these were porosity measures in wells 1 through 7, my goal should be to assess a representative average porosity to calculate the oil in place. That is a great idea. That would be very valuable. I can make decisions. That's inference of the population from a limited sample set. Let's go ahead and do that. What would you think if I told you this additional information? This part of the reservoir is expected to be high quality. This part of the mining resource is expected to be high grade. And this is expected it to be low. Are you as comfortable using the average in order to try to make an assessment of the average? I don't think so. We start to become more uncomfortable. How about now? You see what we had before, now. How's it look? You see, I love good news. Everybody loves good news. The best place to find great mineral grades are in the area with high mineral grades. This can become very dangerous. Why? The assessment of the average property, the porosity, mineral grade, whatever the statistic is we're trying to use to infer the population parameter will start to change. We drilled in the high area first. We drilled a little bit in the low areas. We drilled high, drilled low, and then we kept filling in high values from the high location. Our sample bias will continue to go up and up and up. Clearly, we cannot just use the data to infer the statistics. We need a method to account for the clustering of the data. All right, so let's go ahead and give ourselves a data set. This is a truth data set. If you look, I granted you the superhuman power to be able to see the entire truth, the population, usually inaccessible, but today we're letting you see it. Porosity from 4 to 16%. This is the distribution overall. The true mean is 10% porosity, 10 porosity units. Okay, these are the data right here. How's it looking? Regularly spaced sampling. That looks pretty good. That looks like something, if we go back to our stats 101, should be representative sampling. But if you look really carefully, look at the locations of lows. Here, 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 we're missing data. That has caused a sampling bias. The sample mean, what we'll call the clustered or naive mean, is 10.5 or 4.8. That's an inflation of mean of about 5%. Is that important? 5% inflation in the average porosity would be a 5% inflation of a resource in place. This is sufficient. This is something that could actually impact the economics. We have to account for that. The cell-based declustering method was developed back in the back by Andre Journal. It, in fact, funny enough, was just an addition on an already good paper back in the days when we didn't write so many papers. And this is an excellent methodology. What it does is it takes your data set. Now, can you see my data set? This is a new one. I like this data set. Look at the inferno color bar here, going from very dark to bright colors for high values of porosity. If you look really carefully, you'll see that we have clustering in locations of good porosity. This is a bias, a bias. What we're going to do is we're going to assign a mesh of cells. Now what we'll do is we want to assign a weight to every one of the data values. That weight is going to be based on L naught. L naught is the number of data within the cell, so it's inversely proportional to that. The NL is simply going to be the NL is going to be the number in. Oh, sorry. NL is the number of data in the cell. And L naught is in fact the number of occupied cells. Excuse me, I got that reversed there. And N is just going to be the number of data. By doing this 1 divided by NL, we're going to say the weight we assign to the data in the cell is inversely proportional to the number of data in that cell. And these two terms right here are simply going to standardize the result so that the sum of all weights is equal to N, the number of data. That means a nominal non-clustered weight of 1.0 would indicate that locally the data is neither too clustered or too much samples, nor is it too sparsely sampled. That's a good level of sampling. Now, if you look through, you can figure this out very quickly. 1, 2, 3, 4, 5, 6, 7 data. That would be 1/7 weight standardized by the number of data, number of cells with data, a weight of 3.27. One value would give you a weight of 1.09. If you have a 1, 2, 3, 4 values fall in, you can see how this is working out right now. Now, the declustering weights can be interpreted. Let's take that previous example and we'll calculate the declustered weights. 1.0 is nominal weight. Less than 1.0 is you have a reduced weight because you have too much data. It's clustered. There's too much samples representing that area. And greater than 1 indicates it's too sparsely sampled in those locations. Now, I should note that many software programs use a sum of weights equal to 1 constraint. Not a big deal. That's just normalizing by the number of data. Nominal weight is not 1, but 1 divided by 7. Here's a distribution of the weights for the first scheme of sum of weights equal to n. And you can see nominal weight is there and the overall distribution of weights right there. Now, when we've done this, we can update the distribution. We can update the statistics. Anything we want to do with that data, any statistical analysis can be weighted. In fact, where you look at the naive distribution right here, the histogram, and if you look at the weighted histogram right here, and matplotlib does allow you to integrate a vector of weights to your data easily, you can see that the bars have moved up and down. This is an example right here of probably 1 data in each one of these bins. Right here, you can see it's increased probably 1.5 or 2 data or something like that. It can be fractional now. And you can see over here that this mound, this mode here has in fact dropped and it starts to look more unimodal once we account for the declustered weights. And we can apply it to calculate any statistic. This is how we calculate a declustered mean, the sum of the weights multiplied by the data values divided by the sum of the weights overall. That's a weighted mean. Now, you might be concerned about the sensitivity of the exact location of the cell mesh. This is an important consideration. If you move the mesh around, you see this initial mesh right here. I hope you can see that these 1, 2, 3 data for this offset would all be alone in a cell, but for this offset, all of these 7 data are together. And if you move the mesh even again, it will change the weights. We remove the sensitivity to the mesh position by calculating the weights for each possible mesh offset and by averaging the results. So we'll do like 10 or 20 random offsets in our calculation to remove the sensitivity to mesh location. How do we determine the optimum cell size? There is no theory that states explicitly that we should use a specific cell size. The engineering solution is a very much a conservative solution, and that is if the data has been sampled in a way that exaggerates, that provides an overestimation of the property mean, we will perform an experiment, calculate multiple cell sizes using the multiple offsets, plot it up, and take the cell size that minimizes the declustered mean. That's a conservative assessment. If your feature was in fact underestimated, you had clustered your samples in the low areas instead, this plot would be reversed and we would look for the value of cell size that maximizes the declustered average. Okay, let's go ahead. Let's explore the impact of this choice around the cell size and the offset. Okay, so what I've done, if I go back up here to the top, I've created an interactive spatial data declustering demonstration. It is available on the GitHub account. You can open it up, try it out. You'll need GeostatPy to be able to run it. It's interactive declustering.ipynb. Let's go ahead and try that out. I think this is cool. I put some markdown up here just to kind of explain the context, the idea of clustering. You just need to import GeostatPy, the GeoSlide module, and the Geostats module to be able to run this. And I include a bunch of ipywidgets so that we're able to do interactivity, matplotlib for visualization, pandas for data tables, and NumPy for working with ND arrays. So it should be pretty straightforward. These are pretty standard beside the GeostatPy. Let's go ahead and import that. Here's the declustering routine right here. I have included that locally from the standpoint of I want to be able to run just one cell size. I want to be able to get all of the estimates for all of the grid offsets. I made a custom version of the declustering program to use here locally. Let's run that. Now we have that function available. And I also included from Luca, I took that from Stack Overflow. Thank you very much. It is a weighted percentile calculator. I do think that we should have weighted statistics for everything. And I was a bit surprised that the NP percentile function does not allow for weights. And that would be a great add in the future. Go ahead, and I like to set working directories when we work with a specific data file. Of course, you could replace that with a link to the raw address. If you want that, the data frame is actually available at this address. You could link it to the raw version and you'd be able to load it directly from GitHub if you wanted. And we just multiply by 100 to get ourselves in porosity percentage. We'll go ahead and we're going to do a sampling. The reason we do a sampling here is that we can try out the routine with fewer data for a faster, more interactive runtime. But if you like, at this point, you can go ahead and pick more data. The data frame, I think it originally had something on the order of about 500 data or so. Easy enough to find out right here. I forgot. Let's just go ahead and do a quick check. 289 data. So you could go ahead and change the number of data to a smaller or larger number for your own run. If you have a computer that's a bit slower, come back here and just reload the data and change the number of data, and you get faster runs for the purpose of learning and demonstration. Summary statistics, specify the area of interest. We're going to use the location map program from GeoSlide in some of our runs, and it's not a big deal. It's one line of code, and we're using matplotlib functionality to basically make a nice plot. It mirrors the locmap program or function in GeoSlide that produced the wonderful PostScript images that we all grew up using for geostatistics. Now what we're going to do is we're going to define our interface, and then we're going to instantiate it right here. I think this is pretty cool, in fact. What this does, it takes your subset of data and it puts down an example mesh. Now, the mesh here is 100 by 100. And if you look really carefully, you'll see 100 by 100 cells. It's showing you, in fact, the data weights for this specific mesh if you only use this single mesh. How do we know that? Well, look right here. You see the 3 data in one cell. Its weight's going to be somewhere down here. And if you see right here, we have 1 data value in a cell. It's got a higher weight. So you can see, in fact, that these are the weights for this specific grid location. And then what I've done is it's going to run and give you the declustering, the original naive distribution and naive statistic, the declustered distribution, which is in pink, and its statistic, and you can see the offset. And right here, you'll see the data 1 through 50 with box and whisker plots that show you the range of outcomes for a variety of different grid offsets. Now, you can go ahead and change the number of grid offsets, and you can immediately visualize you're refining those distributions. Now, what are we answering? What question do we answer right now? If you did not use grid offsets, in other words, if you just randomly picked a grid location, your declustered weights for data point number 3 could be all the way from here, a weight of about 0.3, all the way to here, a weight of 1.3. How important is grid offsets and averaging out the effect of the grid location? Essential. Very, very critical. And you can see that right here as we change the number of offsets. Here I'll just do 1 offset, and you can see you get just 1 single value back because we have not looked at the distribution of possible weights. Okay, so that's pretty useful. We can make an assessment of the weights. The average is shown right here as the X, and you can see outliers are pulling the averages outside of the interquartile range at times from the box plot. And now what we can do is we can change the cell size, and we can watch something really interesting. See, the cell size is increasing. The weights are changing for this specific location. And if you look, you can see how the weights are now changing on the box and whisker plots. You can see the sensitivity of not only number of grid offsets, but also the cell size on the individual weights. Now, let's run a little experiment. If I set the cell size as very small, what do you think the weights are going to be? Well, if you look at cell-based declustering, if all the data can end up in their own cells, this is going to take a little while to generate, but that's 5 meter by 5 meter cells. Look at all of the weights. All of the data get equal weight because they all belong to their own cells by themselves. And all of the data here, in fact, do have nominal weight, 1.0. Now let's go ahead and make the cell size very big. If you make the cell size very, very big, let's put it on the order of about 1,000, and we change the number of offsets down to 1 single offset. Now all we have is all the data within a 1 cell like that. All the data get equal weight, and we can see that the data weights are just 1.0. So we can actually explore and understand the sensitivities and how cell-based declustering weights will change as we change cell size and number of offsets. I think this is very good for education and covering these concepts. Let's go ahead, let's go to a proper workflow. I just want to walk through this pretty quickly because I've already talked to you about it. Let me see if I can find it again. Okay, here it is. We have the declustering workflow right here. This is going to be a deja vu opportunity for everybody. It's going to look exactly like, okay, it's going to look exactly like, I'm just checking to make sure I don't have any new messages here. Okay, if anybody has any questions, go ahead, jump in. I am watching the Slack channel. It is hashtag T21-Monday, MON-Geostatistics, and I do welcome any comments or questions anytime. This is a thorough, let's go ahead and clear the output. This is a thorough workflow going through all of the essential steps of cell-based declustering. You could take this workflow with its documentation, put in your own data set, and start performing cell-based declustering. And I think this would be really, really powerful. Here's some explanation up front as far as why do we have biased and spatial sample data. I think that's important to motivate. This time, we're going to go ahead and load up GeostatPy, the GeostatPy, and the geostats modules. Now what we're going to do is we're going to import, all we need is NumPy, pandas, OS. If you want to load locally and set the working directory, matplotlib, and SciPy for some weighted statistics. We'll go ahead and set our working directory. This data file, once again, is available at this link. You can try just linking to it in the read CSV command, or you could go ahead and put it in a working directory like I've done locally. I do that. It's simple for my students. They can do it even if they're disconnected. They don't need to access the server. I think that's pretty useful for my students. The data set we're working with has X, Y, facies, porosity, and permeability. Matthew, I do appreciate the comment. Let me go ahead and I'll show you. The question is cell size for declustering easy to automate to identify the best increment? I will show you the standard GeostatPy method right here where we produce the plot and the algorithm will just find the minimizing cell size. If you are interested, Clayton Deutsch in one of his online tutorials provides some comments around cell size selection, some guardrails. I have a PhD student who's working on use of spatial statistics. That will come out in a book chapter similarly. Would this declustering similarly work on 3D cube of cells? Peter, this is an excellent question. Clustering, cell-based declustering can be applied in any dimensionality. Now here comes the issue. We would usually assign an anisotropy on the actual cell sizes. Okay, what does that mean? The horizontal extent of the cell sizes might be 100 by 100 meters. Vertically, we would do a smaller extent, maybe 1 meter, maybe 5 meters. Now, this is the tricky part. Many people think that should be related to spatial continuity. The answer is no. It is not a function. That anisotropy is not a function of geologic spatial geometric anisotropy. That is whether or not we have shorter ranges vertically versus horizontally, as we often do. The ratio of the extent in the aerial, the horizontal versus the vertical, should be related to the sampling rate. Okay, so if you have an average well spacing horizontally of about 500 meters, but your data is sampled on the meter by meter basis vertically, think of a 500 to 1 anisotropy ratio between these cell extents in the vertical versus the horizontal. Peter, I hope that was helpful to you. I hope that was useful. Let's go ahead and describe the statistics. We always do that. We want to check and make sure that we understand as data as far as skew, outliers, and so forth. This is not a discussion around that. We'll set the extents. We'll do this just for visualization. I love Inferno color bar for people with color issues. It's very good with intensity and tonality changes at the same time, and it does resist bias. Here's the data set we're going to use, the same data set from the lecture slides, and then we'll go ahead and run the declust program. All I do here is just show you the specific inputs that are expected, and you'll see they're very straightforward. Standard Python data frame with the spatial data set. X, I'm just using standard pandas here. X column, Y column. The program that I have here is two-dimensional, not hard to extend to 3D. Hey, if somebody wants to do that, please go ahead and do that. Send a pull request. Let's get it in there and you can start co-authoring open source. Very, very cool. And Peter, thank you very much for the thank you. I do appreciate that. The column for the feature. Why do you need that? The declustering weights are sensitive to the values from the perspective of the selection of the best cell size based on a minimizing cell size. Now, the min and max, you can use 1 if the cell size that minimizes the declustered mean, or you put 0 if you're looking for the value that maximizes, if in fact you have overly sampled the low values. The number of offsets are those random offsets, number of cell sizes going from, are the number of runs you're going to use to produce the plot and find the best cell size, the cell size min, the cell size max. Now, my advice is pick the minimum below the spacing of the data. That will get you back to the naive statistics, equal weighted. The maximum, something much larger than the size of the data set. That gives us exploration of the full data set relationship. Now here we go. Declustering, here's all of the inputs based on our data set. We'll go from a cell size of 1 to 2,000, 10 random offsets, and we can go ahead and make a run of this. We get an output. The output that we get back will include a vector in the same order as the data with weights. We can assign it to our data frame. We now have data weights. Well, the first thing I want to do is I want to look at the data weights. I want to see what's going on. We get the same plot we had before. Now, Peter, I'm curious. I'm interested in what direction you were hoping this would go. I do appreciate the comments and the interactivity here. Let me know if there's something else you want to talk about. That's for sure as far as this topic. It is an important topic. Now, the outputs from this include all of the weights. So we can go ahead and look at the distribution of weights, look at the location map, use matplotlib with no weighting, get the naive distribution, and weight it with our new weights and get the updated. We can also get a vector with the cell sizes and the declustering means for each cell size, and we go ahead and run this. This is showing us diagnostically what was the minimizing cell size. Something around 220 or so was the cell size that was used to calculate these weights. Now let me show you something very interesting. You see how this relationship is quite smooth and interpretable? What would happen if we don't use enough offsets? So let's go and do that. Let's just use a couple of offsets. We can calculate an average from 2 values. We can do that. So we'll get an average over just 2 offsets. We go ahead and run all the way through the workflow, and you see what happened here. The result becomes much more noisy, difficult to interpret. So that's the trade-off. The calculation time of declustering is usually pretty quick. So I just use a large number of offsets. Well, what's a large number? You could use a bigger number than the original 10. Runtime is slowed down a bit. It's technically should be going linearly in the operational complexity. So it'll just triple the runtime from the initial one. And we can go ahead and look, and we see we get a very nice, well-understood relationship. We can pick the optimum cell size. Now, Matthew, does this answer your question right here? I'm going to go ahead and look at the reply there. Oh, okay. Yeah. If you want to use the standard methodology taught in GeostatPy, the tutorial and the handbook, you'll find that this is the standard methodology. Find the cell size that minimizes the declustered mean. In fact, the algorithm that we have implemented from GeostatPy is going to be expecting this label right here, iMinMax, set to 1. It will automatically take that cell size, now calculate the weights. And so these weights come from that cell size. Okay, Matthew. If you're interested, send me an email. I could send you a preprint of my graduate students' work on using spatial data analytics. It does show an improvement on it by using Ripley K, which is fascinating to me. It turns out that that actually does better. It's going to be in a book chapter, so I can always send the preprint to you. All right, let's go back to and let's talk about another important topic. Just finishing up on declustering, and now we'll move into spatial simulation. Now, for those of you who joined in on the last year's open source geostatistics tutorial, you'll notice that I did cover variogram modeling and Kriging estimation. And so my goal is to kind of like cover a new topic, uncertainty, and be able to kind of augment. You can put this all together, the two together, and we actually are starting to cover quite a bit of geostatistics. So I hope this is helpful. Let's talk about, oh, I started at the end. Let me go ahead and go back to the front. All right, I'll go back to the front here, and I'll go ahead and launch that. Let's talk about, oh, that's the wrong one right there. Okay. Okay, there we go. I got to figure it out. Let's talk about spatial simulation. We'll do an interactive demonstration using GeostatsPy, and then I'll show a more complete workflow, and we'll talk about how to summarize and understand, explore uncertainty afterwards, and conclude. Spatial simulation is required to calculate an ensemble of realizations, building block for modeling spatial subsurface uncertainty. It is the workhorse In my experience, 90% of subsurface models had sequential Gaussian simulation as part of the workflow, and the remainder included other forms of simulation, be it object-based, multiple-point statistic-based, or nowadays we're doing a lot of work on doing machine learning-based, but it's all trying to capture the same thing. If you're interested in this topic and you want to dive deeper in, please go ahead and check the simulation lecture that I have available, model checking, how do we check these simulations, co-simulation for multivariate, at least bivariate simulation, which is very important. Let's talk about spatial simulation. The fundamental challenge of estimation is to take an example like this. We have X location. It's a one-dimensional spatial problem for ease of visualization. Y is the response feature, the thing you're trying to model in space. The data points are shown as the black circles. The black line is the inaccessible population. All of the values measured at sufficient resolution from the population so that we could do anything we need to answer any development question. We don't know that. I grant you superhuman power to be able to see it, but then I take that away from you. Now, the red dashed line would be a good representation of an estimation approach. That is trying to get at each location between the data, the very best, the very most likely value. That's the goal of estimation, local accuracy. Now, permeability variance, or whatever you measure, the variance will be too low. Dijkstra-Parsons would be too low for flow simulation. For grade tonnage curves, you would not have enough dispersion. That's called conditional bias in the mining industry. For the purpose of groundwater, your conductivity would just be wrong, and you would not have the same degree of perhaps advective and diffusive flow with your contaminants in the subsurface. It would just be wrong. What do we accomplish with simulation? Conversely, what we do is we take that data and we produce conditional simulations, realizations. Blue and red are two realizations. Now, please sit back from your computer. This is time to kind of reflect. Look at those images. Can I convince you that the blue and red image, those lines, have the same spatial continuity, very similar histograms, variance, the means, the P10, the P90s, would all be very similar to the black line, the truth that we do not have. That's the whole point of simulation. In fact, does anybody on the call like dill pickle potato chips? Anyone a fan of them? I thought they were only in Canada, but I was happy to hear that you can find these, in fact, down here. Matt and all my friends up there in Canada, you know, dill pickle potato chips along with ketchup are very much loved, right? Now, you'll notice this is, in fact, a Canadian package. It does have it in French, but the English side uses the term simulated flavor. That's why I like this bag of potato chips. Now, what does it mean to have a simulated dill pickle potato chip? Do you imagine that there's a big factory and in one side, truckload upon truckload of dill pickles, and on the other side, potato chips coming out? Is that what you imagine is happening? Would you be shocked if I was to tell you and reassure you that not a single dill pickle was harmed to make this product? Would you agree with me? I think so. That's why we say simulated flavor. If we simulate the subsurface, what does that mean? It should look, taste, feel, perform, behave like real subsurface. It doesn't mean it is the subsurface. It means it should actually just behave like the subsurface. A simulated reservoir should flow like a simulated reservoir. Groundwater, hydrocarbons, or if it's mining, it should mine like a real mining deposit. That's the whole point of simulation. That means that we have a paradox. We are being pulled between two fundamentally different problems. The two problems are spatial estimation, spatial simulation. Let's walk through them in this table. This is a good summarization right here. On the side here in the rows, these are fundamental criteria for subsurface models. Local data conditioning, the Kriging term would be exactitude. At the data locations, you honor the data. Estimation and simulation do that. In fact, if you go back here, if you look here, you'll see that both of them, the simulated realizations and the estimations, pass through the data at the data locations. Exactitude is not a problem. Local accuracy, the best value, minimizes estimation variance. I'm not going to cover the derivation or discuss estimation variance in detail, but that is the idea of the error at the local estimate. Now, if we go right here, let's just think about this. This red line is minimizing the error in between the data. These are the estimates, each one of them individually, of least astonishment. Now, the simulated realization, could we all agree together that this does not minimize the estimation variance? By no means could we consider this to be the most likely value between here and here. Okay, so everyone see that the simulated results sacrifice local accuracy. Okay, now spatial continuity. Let's go back and look here. If you look at the data, the degree of spatial continuity from data to data, we could calculate the variogram, we can model it, produce a variogram model. I hope you can see that the estimation is always going to be just too smooth. For those of you who do geostats, it behaves like a Gaussian structure. It'll behave like there's no nugget effect, and it will inflate the range of the variogram. Okay, these are all very, very important. Now this spatial continuity, step back and look at that model, and you'll see that it has the same degree of undulation, short scale continuity. You see how it's changing locally? It does it like the real data. You see how it changes over the long range? That is like look at these undulations. Those are captured in the simulation. We get spatial continuity back and uncertainty model. The Kriging approach will give us the best estimate at each location with an estimation variance uncertainty model, local uncertainty. But there's only one model. That's not global uncertainty. The simulation gives me one realization, two realizations. I can run them all day. I can do this all day. Hundreds of realizations, each one of them could be analyzed. That is a measure of global uncertainty. This is the trade-off between estimation and simulation. Let's focus on simulation, but let's compare and contrast a little bit more, put you a little more details on for you. Global versus local measures. A local measure, that's the feature value at a single location. The global measure is a statistical summary over the volume of interest. Okay, so the global distribution, the global porosity variogram, the flow rate or the recovery of hydrocarbon or mineral grade, those are all global measures of model performance. Global versus local accuracy. Now that we've defined this, global accuracy is we honor the statistic calculated over the volume of interest, the variogram, the distribution, the recovery, and so forth. Local accuracy is we have the best estimate that minimizes estimation variance, the most likely value at each location. You cannot do both. You cannot build a model that has the best global accuracy and local accuracy. You have to pick one or the other. If you pick local accuracy, you're doing estimation. If you're doing global, you're doing simulation. Sequential Gaussian simulation. The fundamental workhorse in simulation, it has three important components. Sequential, you sequentially include simulated values to impose the right spatial continuity between the simulated values. Gaussian, you work in Gaussian space. That ensures that we honor the global distribution, and with the Kriging variance and the Kriging estimate, we know the local distribution of uncertainty, so we can do Monte Carlo simulation. Monte Carlo simulation is the simulation aspect. We're going to draw randomly from local distributions of uncertainty to add in to get the missing variance, to get the right distribution of uncertainty globally, and also to build multiple realizations. It's Monte Carlo simulation. That's why we say simulation. Okay, woo, that was a lot of work. I don't know about you all, but I hope everyone, how's your energy level right now? Welcome, Ed. Are you guys all doing well? We're at 1 o'clock p.m. We're technically the halfway point. Let me just ask, are you all okay if I show this demonstration and then we do a short break after that? During the short break, we can have discussion. Is that okay? Thumbs up in the chat window. Anyone okay with that? Okay. I know there's a bit of lag. I'll go ahead and start opening things up. Now, anyone who takes my classes knows I'm quite democratic. You can make me walk the plank at any time. You can literally tell me, you know what, we're tired. We need a break right now. And I will stop. But I'll assume that we're good to go for now. I'm actually kind of proud of this interactive Python workflow. It's interactive sequential Gaussian simulation. It's the best way to learn sequential Gaussian simulation is by playing with it. Now, the other thing that I'm very proud of is that while I put a bunch of documentation explanation of sequential methodology. Matthew, that's so funny. Thank you very much for that comment. I can be paused on YouTube and people can come back and just keep going. I never realized that. So technically, you all have permission to take a break anytime. But you'll miss out on the live real-time extravaganza that is this tutorial. So I'm just saying, stay with us if you can. Okay, I cover all of the fundamentals of kriging, spatial continuity, sequential Gaussian simulation, and I link lectures for you. Okay. Brevers, I really do appreciate this. You asked about my book, Pyrcz in Deutsch, section 5.3.3, where we talk about the number of realizations that are required. I can make some comments around that. I would agree that that was an effort to apply objectivity to the important question of number of realizations. My experience has been that given all of the geologic scenario-based considerations, that in fact, number of realizations is an insufficient way to consider exploring uncertainty. In fact, we should be thinking of having a reasonable number of realizations for a large set of scenarios. And so I'll tell you what, I'll make a couple more comments at the end, but I do appreciate the reference to the book in that section, and I do appreciate the opportunity to discuss that a little bit more in a bit. Okay, GeostatsPy, we're gonna go ahead and bring that in, GeoSlib and Geostats modules. I'm gonna go ahead and load up a bunch of stuff here. ipywidgets for the interactivity. I'm a big fan. I love this stuff. It's been a lot of fun. I've kind of made a lot of interactive workflows on my GitHub account. Matplotlib. We're going to need patches. You'll see I put a little bit of fanciness with some ellipses on the plot, SciPy stats, so we can calculate the Gaussian distribution to show the target and the result. And we also do NumPy and pandas as always. Okay, let's go ahead and import that. Simple kriging. If anybody thinks that's kind of funny, it was supposed to be. What I did was I took GeostatsPy, I took out the simple kriging program, and I made a very simple one in which I could go ahead and perform kriging just at specific locations. It's a fast, sped up form of kriging that we can just do at locations, not over an entire mesh. That was important for this workflow. We're going to specify our grid extents. We'll do that there. You can see right here that we've created a specific grid size. We'll go ahead and instantiate a dashboard, and now we have our dashboard. Now, I'm going to jump through this. I'm not going to go through all of this right now. I'm going to go through the next one. But for those of you who are interested, what you can do here is you can specify the variogram range. Let me go ahead and reduce that a little bit so you can see it. Put it in the model. There we go. 500 meters. We'll go ahead and we'll have an unknown location. We'll have a data location here, here, and here. And we have the simulation locations shown by the circles. You can even move the data locations around. You see I just moved it. You can set the variogram model. This circle is just giving you a global indication of the variogram range from the center just for visualization. I can prove it to you. I can go ahead and rotate it. If I rotate it, you can now see spatial continuity. You can see the variogram models over the different directions, the major direction, the minor direction shown right here. And now what we can do is we can go ahead and use this to be able to calculate the simulated realizations at a set of discrete locations. Now, I hope what you can see is with that spatial continuity, and if I rotate it kind of around, you can see that this value is low. It has a low value there. And now I'm causing a continuity through those points of low values. This is kind of, high, and this is the low value here. And you can see the spatial continuity. You can increase the nugget effect here. And you can start to see that we've destroyed the spatial continuity. Okay, so I said I wasn't going to talk too much about this. This is doing sequential Gaussian simulation at a range of different points. Now, I want to go on to right here, and we're going to do it on a grid. This is the most common application of sequential Gaussian simulation. We're going to spend a little bit of time here. I think this is really helpful. If you have this loaded up locally, I welcome you to run to this point, go ahead, get to this display, and we'll walk through it together. If you don't, we'll talk about it, and then go ahead afterwards, load it up directly from the GitHub repository for this tutorial. Try it out on your own time. Let me explain the dashboard in greater detail than what I just did. Number of cells. This is simply 20 different cells at which we will do sequential Gaussian simulation. Now, let me show you. I could put it to 100. This is a 10 by 10 mesh for brevity or for fast run times. But can you see, even with my machine, it's a pretty modern machine. It's a good desktop. I have a pretty good CPU on it. Still takes a long time to run. By decreasing the number of cells to a smaller number, like say 30, you get very fast run times, and you can do some visualization, understand what's going on. Let's go ahead and do that. What's interesting is the operational complexity is actually going up. It's going up to a power of the number of cells, and the reason being is the fact that it's a sequential simulation approach that has more and more data for the Kriging solution as you go on, and that does cause, I believe it's actually an O3 operator. So that will cause it to go up quite a bit as you increase the number of cells. The runtimes are going to increase. Okay, you can go ahead here and you can change the spatial continuity. Now, if you look really carefully, what you'll see is you see how the yellow, blue, and red ellipse have moved around. I'm going to move this data point further away to the side there. You are now seeing the range of continuity around those data points. I can go ahead and decrease that a little bit so you can see it on the model a bit better. See right there? That's the distance of continuity. Let me increase the minor direction of continuity, and it becomes wider. You can see these ellipses around the data. Green, red, and blue. Green, red, and blue data. You can, in fact, move the data points around and see how the model updates. Okay, I think this is pretty useful. Now what we can do is we can go ahead and change varogram parameters, and we can immediately observe the impact on sequential Gaussian simulation. This right here is the simulated values coming out. It does the forward and back transformation. So it transforms your data to Gaussian, standard normal, then it does the simulation, it back transforms. This is the target distribution given that, and these are the actual resulting values right there. All right. Okay. I saw somebody ran into an error. I do appreciate you sending that to me. I wouldn't have time to try to figure that out. What I'm going to do is I'll take a screen capture of that and I'll take a look afterwards. Let me know if anybody else is running into an error like that. And I can check it out. If you don't mind, Juan, could you go ahead and just let me know what version of NumPy you're using, and I'll make sure it's not a version issue or something like that. I appreciate that. Thank you very much. Okay, so we can go ahead now and run some experiments, and we can immediately see spatial continuity, how it impacts the model. First thing is, if you add nugget effect, if I increase the relative nugget effect right here, what I'll see is that the spatial continuity from cell to cell is being disrupted. 50% relative nugget effect, 70% relative nugget effect, 90% relative nugget effect. By the time I get to 100% relative nugget effect, I hope you can see that we've basically broken up the spatial continuity between the cells. Now you can change this random number seed and get a totally different model. And do you see what happened? All of these locations can vary over the entire distribution. Let's go ahead and visualize a couple more. And you can see now the other thing you should notice is that the random path is in fact a function of the random number seed. And so the specific 50 cells that are simulated is also moving around and changing. Now I want to also point something else out very important. Who here on the call is familiar with the concept of ergodic fluctuations? Anybody ever heard of ergodic fluctuations? In geostatistics speak, what that means is that the actual statistics are honored, but with fluctuations. Now, what we know is that as you increase spatial continuity, the degree of those fluctuations is going to go up. Look at the realization mean, 17.46. Look at the input mean right here. Now, if we go ahead and change the random number seed, look at how it varies. 17.46, 17.41, 16.57, 16.8, 17.2. Do you see how it has stochasticity, ergodic fluctuations around the global mean, the target mean? We have a 100% nugget effect. That should be very small. Now let's go ahead and remove the nugget effect. We're going to add spatial continuity in. Let's go ahead and increase the range of spatial continuity significantly. Do you see what happened? We now have great spatial continuity, very smooth looking realizations. Now we can go ahead and look again at the results here. Let me just increase the minor too. Okay, we'll put lots of spatial continuity in. We got 16.48. Now we run again. 17.2, 17.5, 16.9. What's happening now, if you look carefully, is that we should see a higher degree of stochasticity. We've seen values as high as 17.8. We've seen values around, I believe, about 16.3 or something like that, 16.5, 18.3. The mean is fluctuating even more, and the reason being is that we have a high degree of spatial continuity. Now, if anybody here is into the theory of geostatistics, you can calculate the anticipated degree of ergodic fluctuations in the mean as the dispersion variance of the model within an infinite domain or within a large volume. Okay, and so that would actually give you that value. We can start to make these types of observations about sequential Gaussian simulation by running multiple realizations, exploring them. We can start to see spatial continuity. We can see reproduction of the histogram and so forth by running many models and exploring and playing with the machine. Okay, I welcome any comments or questions about this. What I'll do right now, what is a break running for right now on the Transform 2021 conference? I'm going to guess about 5 minutes. So why don't we go ahead, we'll come back at 1:17 and we'll continue on live if you want to be live with me. Of course, you can pause at any time if you want to take breaks otherwise. Okay, I'll be watching the Slack channel. If there's anybody with questions, I do welcome those questions. Juan, what version of NumPy are you running? I'm curious now. I want to know what's going on there. All right. So I hope that this was an interesting discussion of sequential Gaussian simulation, a live demonstration of a simple, interactive, two-dimensional sequential Gaussian simulation on a grid. The workflow also includes the ability to do sequential Gaussian simulation on specific points in space. And you're able to do all kinds of things to explore and understand spatial continuity. Change the variogram range, add asymmetry or anisotropy, rotate and change the directionality as the anisotropy. And you'll notice that if you use the full grid, that there is, I believe, an 0.3 increase in operational complexity, resulting in computational complexity, resulting in much slower run times. So you can use smaller numbers for fast investigation and experimentation. It's good to play with sequential Gaussian simulation, understand its behavior, and even up to and discuss the concept of ergodic fluctuations. Now what I'll do is I'll provide a walkthrough of a more comprehensive workflow in simulation. Then what we're going to do is we're going to take that result and we're going to propose some post-processing methodologies that were covered in the book with Pyrcz and Deutsch back in 2014 and are available to you easily using Python workflows methodologies. Okay, so we're going to go ahead and do a walkthrough of a full simulation workflow. Let me go ahead and open that up right here. Oh. No, this one right here. Okay. And I'll make sure I'm looking at the Slack channel in case there are. Okay. Okay, it looks like it's running for you now. Thank you very much. So it looked like you did. Okay, so you used NumPy version 1.17 and it works fine. Okay, and you're suggesting a comment around. If you want to send a pull request or just send me an email directly, I really appreciate you identifying this issue with a more modern version of NumPy, and let's go ahead and get that fixed. I do appreciate the assistance. Thank you. Okay, so this is a more comprehensive workflow right here where we're doing two-dimensional realizations of sequential Gaussian simulation. We will add at the end some post-processing. This is available on the GitHub account with all of the other workflows. It's more of a walkthrough. We can walk through it together, discuss it. We can make some changes, rerun, and so forth. Should be kind of interesting. We're going to start out by importing GeostatsPy, Geostats module, and the GeostatLib module right there. We can go ahead and import OS if we want to set for matrix math and arrays, pandas for tabular data, the data frames, and matplotlib for plotting. And we'll use that throughout. We're going to set some functions right here. Now the functions we're declaring here should actually be added to GeostatPy, but haven't been added yet. And they include local expectation, local standard deviation, local percentile. These are model post-processing methodologies. We'll go ahead and import them. We'll go back to the content, the course lecture notes, and then I'll come back and explain them. Let's go ahead and read in a data set. We'll do just a minor amount of feature engineering, not a big deal. All we're going to do is convert the porosity values from a fraction to a percentage, and we'll also do a ln, natural log transform of permeability values. So we have a log permeability that we can work with too. We're going to resample the data. We do this because we just want to test different data sets. You can have different runs. You can see how it looks. We're going to explore uncertainty. And one of the best ways to do that is use sparse data and see the uncertainty. Come back here. Remember, there was about 200, I believe there was about in this data set. Let me just check. I want to make sure I know exactly how many data we have available here. Length, data frame. We have 367 on this data set. So you can vary the number of data you're working with from 10 or from something very small to something very large and see how it impacts the global uncertainty model you're about to be looking at. We'll come back and do that. So let's go ahead and resample 10 random samples. We have a new data frame that has been sampled. We reset the index, so we've got everything just nicely indexing across 0 through 9. We're going to specify the model parameters. Now, there's a lot here to work with, and I'm not going to spend the time I should on it, but I will just say that this first part right here is just the grid specification. And those of you who are familiar with GeostatPy will recognize the specification. Number of cells, the size of the cells, the min value, MN, is actually the cell centroid in the lower left corner. Now, GeostatPy uses an indexing where the origin of the grid is the bottom left corner, unlike NumPy, which uses the top left corner. So just imagine that that'll be the cell in the bottom left corner. The centroid of it is 10 by 10. That means our actual origin of the edge of the grid is 0 by 0. And if you look right here, you'll see the cell sizes are 20 by 20. And if we have 50 of those, this is a 0 through 1000, 0 through 1000 grid in both dimensions. Okay, we got Vmin, Vmax. That's just for visualization of the color bars. Now, here's where things get a little more deep into the sequential Gaussian simulation world. NDmin is the minimum number of data to use to simulate at a location. We set it as 0 because we're okay with using the global mean and using previously simulated values. NDmax is a constraint on runtime. If by using too many data at a location, we increase the Kriging matrix size, and the versions will go up once again to a computational complexity of 03. Node max is the maximum number of previously simulated nodes to use, and NXDis, NYDis is if we want to do a volume-based approach, and we're not doing discretization, it's just one. The radius is the ultimate maximum distance at which we'll collect data. Kriging type 0 is just going to be simple Kriging. And because it's simple Kriging, we have to put in a simple Kriging mean right here. Okay, now we're going to go ahead and specify a variogram model. And these are all the parameters we need to be able to run this model. The Geostats sequential Gaussian simulation routine is shown right here. Unfortunately, there is quite a bit. And I know I've created a monster list of arguments, and I do apologize for that. There's probably be better to break it up into class structures and to have specific classes of inputs that are more manageable, or even just dictionaries or something to kind of simplify this, break it up by grid specification, search parameters, and so forth. I apologize for that. That should be improved. This is what it looks like. To those of you who've seen GeostatPy run in Fortran, you will right now be having a sense of nostalgia and fear. I mean nostalgia. No, you'll just feel nostalgic and happy to see it. And then at the very end, we ran a very simple function to be able to produce what looks exactly like pixel plot from GeostatPy. So we have our nicely labeled, you can see the data values right here that conditioned the model. We can go ahead and see the porosity color bar going from 0 to 30% porosity. And you can see, okay, can you see the spatial continuity? Can you see the directionality? What's the major direction of spatial continuity? The y-axis is 0, 0, 0, azimuth. The x-axis is 0, 9, 0. Would anyone agree with me that it looks like probably 0, 4, 5 or something like that? We can go ahead and go back here. And if we look, I was close. The major direction continuity has a range of 400 meters. The minor has 200 meters. That's a 2-to-1 anisotropy ratio. And the azimuth is 60 degrees. So a little bit more than 45. And if you go back and look, you can convince yourself that that's probably the spatial continuity right there. We report back the mean in Gaussian space. It's good for checking. Are you close to standard normal? 0. We also check the variance. Now you would expect that given the sill as the variogram is equal to 1, as it should be theoretically, that in Gaussian space we should be close to 1.0. Now what's very interesting here is that these are the source of ergodic fluctuations. If we do multiple realizations, this will change. And we're going to see that with different values, the back transformation from Gaussian to regular space will cause shifts in variance and centrality, the central tendency of the distributions. Now, Pyrcz has a good question. Is there a parameter to choose the type of Kriging used, simple versus ordinary? Yes, we did. We went ahead. I did code up the ability to make the choice between Kriging types. I'm just looking for it right here. Kriging type, K type. If you go to the original GeostatPy, K type of 0 is simple Kriging. K-type of 1 is ordinary kriging. Now, just one thing I should note is for this version, I did remove universal kriging. Kriging with a trend is available though still, but there's no universal kriging where we simultaneously fit polynomial parameters at the same time as performing local kriging. We haven't done that in this version. Pyrcz, thank you very much for the question. I appreciate that. Okay, so we go ahead, we can calculate geostatistical realizations using sequential Gaussian simulation. Now let's go ahead and loop it. All I'm doing here is looping over a number of realizations, 9 realizations. I'm going to go ahead and explicitly set the seed number, my favorite number, 73073 for a seed number. Don't worry, it's just superstition. There's no, any integer is fine, plus I real. And that allowed me to create unique realizations for each one of the runs. Then what we're going to do is we're going to loop over them, and we're going to do that plotting method, the function I declared at the very top, and we'll go ahead and plot them all up. Now this is instructive. Realization 0, that's the first run for that specification, the first one. Now I haven't been careful here to set these indices, but if you look, we have a mean of now 1.8, a pretty good departure from 0, and 0.67. Now, those of you out there who are like, wow, that seems like a lot of ergodic fluctuations, there is a complexity here of a limited model size, spatial continuity range, which is pretty high, and in addition, data conditioning. Data conditioning can have a anchoring effect on simulated realizations with good amount of spatial continuity. Here we go. Ooh, the variance is close to 1. The mean is much lower now. That's interesting. Mean is close to 0. The variance is significantly less than 1. You're now seeing ergodic fluctuations. Here we go. Now we finally got a mean that's a little bit below 0. I think personally the values of the data are kind of pulling it up a bit. Maybe we have kind of a systematically high set of values and the model variance is low. Here we have a slightly negative again. We can look through these. It's not a bad idea to check, to look at the degree of fluctuation. Now let's go ahead and look at and compare multiple realizations. This is a great thing to do. Get a sense of what's going on with our data sets. What is the spatial uncertainty away from the data derived from histogram, varogram, and under the Gaussian assumption of sequential Gaussian simulation. Now, if we look at the data locations, that's a moderate value right there. Look at the data location, moderate value right there, moderate value, moderate. Do you see what's happening here? The data conditioning is working. Every time we go to that one data point, we do get values that are pretty low, pretty moderate, kind of moderately high. If we look at this location, this is a low value, low value, low value, low value. Look at the spatial uncertainty away from that location. We have realizations. The azimuth is 0, 6, 0 is the major direction. We have locations where we see low values all the way out to here. We have locations where they come out to here, here. We can see that this is informing a local low, but the stochasticity, the uncertainty away from the data is still quite high given the spatial continuity model. And we can have cases where it's low like that, cases like this. We're seeing the differences between the realizations. Now, this is known as spatial uncertainty. Even if I know perfectly the histogram, the varogram, and the values at these circles, at the data locations, we still don't know the values in between perfectly. Would you agree with me? If we know it's fluvial, we know it's aeolian, I know the porosity goes between 0 and 28%, I still don't know perfectly what's going on between the data. Multiple realizations is our way to capture the uncertainty in between all of the data values. Okay. Questions or comments? Pyrcz, thank you very much for that. Thank you. And I do appreciate your level of participation and assistance in the tutorial. You know, these things are a community effort, and I do appreciate even looking at code. Juan and Doug looking at code. I appreciate this very much. It just really is just so much welcome. Okay, so let's go ahead and talk about model summarization. I'm going to go ahead and open up another slide deck. And we're going to talk about how we summarize uncertainty models. Okay, spatial simulation post-sim. In the book with Deutsch in the GeostLib library, there is a post-sim set of algorithms that I'm going to demonstrate using the GeostatPy package. The idea is this. I showed you multiple realizations. We could change the histogram. I could produce a bunch of models. But at the end of the day, models, we need to communicate spatial uncertainty. Okay, let's go ahead and look at spatial simulation with post-sim. Motivation is this: we have multiple realizations. We need to visualize and communicate uncertainty. We need practical workflows that summarize spatial uncertainty in our geologic settings, in the subsurface, or any spatial setting. Local uncertainty maps provide a measure of local uncertainty suitable to support decision making. We'll talk more about this, but I think this is a very, very powerful thing to do, and I don't see this often enough. Declustering, I don't see often enough. Post-processing for local uncertainty, I don't see often enough. Okay, what's the idea? The idea is very, very simple. We're going to go ahead and we'll take multiple realizations. 1, 2, 3, 4, 5. Well, we had 9. We're going to calculate more like 20 based on the amount of time that we have available to us. We're going to scan over all the realizations and scenarios. In my workflows, I'm not showing scenarios. It would be easy to do. Just make a different modeling choice and build a bunch more realizations and put them together, compile them together. Calculate the local distributions of, we're going to calculate the local distributions of uncertainty at each location. We'll calculate the statistical summary over each location and place in a map or a model. Now we're doing maps today, so it'll just be maps. This is easy. Okay, what are we going to do? What is the specific percentile outcome at this location? How would I calculate that? Well, it turns out that if I have 1, 2, 3, 4, 5 models, I can pick a location. And if I take all the values at that model, that model, that model, that model, that model, that same location, and I put them into a non-parametric CDF, would you all agree that that's a distribution? That's the distribution of uncertainty at this location right here. Now what I can do is I can calculate any percentile value. Now I hope you can see very quickly that if I don't have enough values available to me, it's going to be a pretty noisy result. It'll be very difficult to interrogate and look at. But we'll calculate enough realization so we can do that. And so that is the local percentile outcome at this location, or what is the specific percentile at that location. So we can calculate the P90, that would be like a P90, P10, P50, P13, whatever percentile value I want. And we can communicate that. Another one is, what is the local probability of exceeding a threshold at a location, or the risk of not exceeding a threshold? That's super easy to do. This right here is the inverse of a CDF, shown right here. This right here is the opposite direction. It is the forward of the CDF. We can go ahead and calculate what is the probability of having a value that is equal to this or less. That's the probability of exceedance. We can go ahead and, that is the probability of exceeding that value, and that can be calculated just by taking the cumulative distribution function. Now we can do the opposite, and that's the risk. That's the risk that we have a value that in fact is going to be even higher than that. And so we can go ahead and calculate that as 1 minus the cumulative distribution function. So we get the probability of an actual realization. We can get the probability of an actual realization being greater than the value like this, a threshold, or being less than the threshold like this, both of them using the forward on the CDF that we've calculated experimentally. It's a non-parametric CDF from the realizations, and very easy to do. So let's take an example. We'll take those realizations we just calculated. We have the realization shown right here. And we can go ahead and, if anybody has this workflow opened up in the background, I welcome you to change the variogram model. change the proportion nugget effect and rerun it and just take a look at it. It does take about a minute to run, so I didn't run a bunch of examples, but please feel free to run that as you're listening to, and we're talking about post simulation. Now what we can do is we can take all of those realizations. We had 9 realizations. At each location, I can calculate the expectation. Now, expectation is just a probability weighted average. So I can go ahead and just take, if I assume each realization equal probable, this is an average. Now, within the GeoSlide book, they call this, and GeoSlide code, they call this an E-type model. The expectation, local expectation. Now, is there anybody in the room who's wondering what's the difference between an E-type model or expected local value versus kriging? Turns out they're almost the same. The only thing that changes is the fact that we've done a Gaussian transformation. We're working in Gaussian space. A Gaussian transformation is nonlinear. Therefore, the expectation may be shifted versus the regular kriging estimate for sure. Then what we can do is we can calculate the conditional standard deviation. I think this is very, very powerful. If you look really carefully at the data locations, we should have very low conditional expectation. It should be darn near 0. That's because at the data locations, the realizations from realization to realization should not change very much. Now, away from the data, we get more degree of dissimilarity. Now, there is some structure in here, probably driven by the fact that we don't have enough realizations to inform this map. If we did a lot of realizations, this would eventually smooth down. Okay, so we can do that. What are we going to do with that? If I calculate the local conditional standard deviation, it is a measure of the local uncertainty. What people will do is they'll use that if you've incorporated all of your data into these realizations. Now I know the locations where I have the maximum uncertainty, and I've seen people choose to sample those locations. I've also seen in the mining industry, people will use these types of maps to assess proven, probable, and possible assignments for resources in place. And so, or reserves. And that's been done where you basically say, where we have a low uncertainty, we are certain, we have a low uncertainty, and we have an expectation that's high, we have a low risk of having a bad resource. We can go ahead and assign that as being a resource that we've proven up to some degree. That's a geostatistical approach for a resource. Now, making that statement, I'm not claiming or teaching anything around resource allocation. You have to look at local guidelines, SEC and so forth. And so please don't use what I've just suggested. I'm just making comments on possible applications. Okay, that's my fine print. Now we can also do local uncertainty. Remember where I showed the local percentile values. Now, when I do this, look very carefully here. It's labeled as local P10 model. What does that mean? It's not the P10 model, okay? Because the P10 model would be based on some type of criteria globally. This is at every single location. I took the P10 outcome from all the realizations. If you use this as a P10 model, this would surely be very pessimistic because we took the P10 at each location. Everybody knows a P10 of the P10 of the P10 of the P10 is not a P10. That's more like a P0 point something. It'd be very low. This is the local P50. This is the local median model, the local P90. What are we going to do with this type of model? Now, this is very fascinating. If we look here, we have a P10 value locally. That's actually pretty high. That tells me that's a location that is surely high because there's a 90% probability of it being even higher. I think that's a very powerful communication tool. Here we have a location that the P90 model is low. Well, that is surely going to be low because there's a 90% probability that it's even lower than that. Okay, so I think these are all very powerful concepts. Let's go ahead and walk through doing this approach of summarization over multiple realizations. The workflow that I provided, that I have available to you, is this workflow that I was just showing you just now. We created our 9 stochastic realizations and we looked at them. Now what we're going to do next is we're going to take those models and we're going to say local expectation function. It's going to go through every one of these models. This cell, this cell, this cell. Literally, we're taking the average over all values in the same cell location, and then we put them in that cell. So when we run this code right here, it should run pretty quick. It's just going to go over those 9 realizations and give us the average in every cell. This is very straightforward. Now, if you're doing scenario-based approaches where the probability of scenarios vary, you should account for that with a probability weighted average based on the scenario information. For sure, that would be very important. We can also look at the local standard deviation. The conditional standard deviation is often shown as conditional variance. I like conditional standard deviation because it is in the units of the feature of interest. It becomes easier to understand. Even you can start to think, the expectation plus or minus 3 standard deviations, assuming a Gaussian distribution to cover a specific possibility or alpha level. You can start thinking about it that way. The local percentile models are shown right here. This uses local percentile, will be put directly into GeostatPy. I think it's very convenient and useful. The realization models, P10, P50, P90. I'm going to go ahead and run those right there. That's how we got those results that I showed you above. Now, of course, you can start to ask questions like a local P1 model. Now we can see these are the cases, wow, this high value here is still high around here, indicating there's a 99% chance of being even higher now. So all I did was just create a P01 model and ran it. So you can look at different percentiles, local percentiles. Many companies have a P10, P90 reporting, and I think this is a very good way to look at local uncertainty from simulation. The workflow I showed was very simple. You could have trend models. You could have secondary information integrated. You could be putting it all together, and now these local uncertainty models is showing you the value or impact of all of your different information sources, secondary soft information, well data, or local samples, all of them combined together. What about the probability of exceedance? So what I've done is I put in values of porosity, 11%, 13%, 18%. This is the probability of having a porosity greater than that value. So we go ahead and run this. And what we can see right here is, in fact, now I'm seeing something. I'm recognizing the fact that, yeah, this is the probability of porosity values greater than the thresholds. So 11%, 13%, 18% right here. Now, this is very cool because if you look, 11%, 13, and 18%, the probabilities globally are dropping because you have a lower probability of exceeding the threshold. The threshold's getting higher and higher. And we can use this. Now, what are we going to do with that? Perhaps there's a critical economic threshold. I need a certain value. Perhaps there's an environmental threshold that if I exceed a certain value, that means I have something reportable. It's considered to be a contaminant or something like that. This is all very useful to help us be able to build these types of spatial uncertainty models that we can use for business purposes. Now, what's very interesting, or decision-making support, is if you look at the data locations, data, that's hard to see. I admit with the color scheme, it's hard to see. Another data over here and so forth. I think one up here. You can see it on that map. What's very interesting is if you look at the data locations, what are the values going to be? What's the probability of exceeding 11% at a data location? It's going to be either 1 or 0. Do you see that? Because you already know the actual value. There's no uncertainty at those locations. Okay, that right there is a demonstration of summarization of uncertainty over multiple realizations. I think that's a very powerful methodology. Let me go ahead. I'll make some concluding remarks and finish up here. I do apologize. Right at the end time of this webinar, of this tutorial, I need to be giving a lecture at the University of Texas at Austin. So I'm literally going to run out like just a minute or two before so I can run into my lecture and give that lecture. Let me make some concluding remarks. What's the motivation? I really want to promote the use and contribution to GeostatPy. Doug, Juan, and others have been contributing even during this tutorial. detecting and debugging issues in the package. Very much welcome. I do appreciate that. This is all very, very important. Support education, students, working professionals, and potential students. Encourage people to go into STEM. That's my goal. If you look at my content online, I share every lecture. I'm all about removing barriers and supporting people, helping out, providing a lot of software and workflows to support people. This is all part of the GeostatsPy, fits perfectly within that. Expand the use of spatial data analytics and machine learning in the subsurface. I would like to see more being done, and make spatial data analytics and machine learning workflows accessible to all scientists and engineers. I think we have this opportunity together. Okay, I do give appreciation. I should add, I could even right now start to add names of people, Juan and Doug and others, who are noting and indicating issues that can be corrected. And so I would love to see this expand. Let's continue working together. What is good? Well, I think it's a pretty good base package for getting the job done. I think there's a lot of people I'm hearing about around the world who are using it to do things. There's great interactive demonstrations that can be useful, and it's available on PyPy. So and also on GitHub, you can see the entire code base is available there. So anyone in the world can access it. It truly is open source. What needs work? Well, of course, documentation improvements. Expanded spatial data analytics, spatial statistics, efficiency optimization, support for three-dimensional workflows. And I think we've seen demonstrated here today, to some degree, maintenance to keep us up to date as NumPy and Pandas and so forth move forward. I saw one of the issues was vert was deprecated and removed from some specific plotting functionality in matplotlib for doing vertical exaggeration of plots. All of these things, it's important to kind of keep up with the new developments as we move along. More resources on subsurface data analytics and machine learning. Well, go ahead, check out my GitHub account. I have a lot that I share there for anyone in the world. I have all of my lectures available on my YouTube channel, and I do daily share technical information, positivity, and so forth, resources with the community on Twitter. And I do enjoy doing that and interacting with people there. I am a professor. It means I have my hat in my hands at all times. I have a direct consortium where we do subsurface data analytics and machine learning with Dr. Foster. We work directly together with a range of companies there. Let me know if your company is interested in participating, collaborating with students, working through a consortium. And I do a lot of education for professionals through Datum, the startup company that I co-founded with Dr. Foster. Okay, that's it. Now, if anybody's interested, I do welcome feedback on this tutorial. What did you like? What's the plus? And general comments or deltas. Is there something that you feel should be improved or could be improved for next time? I, of course, welcome that. I'm always happy to find opportunities to improve and to support the community. All right. Other than that, I do welcome questions at this moment.
If there are any questions, please feel free to write them into the Slack channel. We have a few more minutes of time left. If I don't see anything in the next few minutes, and Michael, we'll just conclude the session, okay?
That's great, Ashley. Ashley, thanks for all your wonderful support with this. I do appreciate everything that you're doing to support Transform. This is awesome. What a great venue for sure. Yeah, if nobody asks anything, I will run off and give another lecture here.
Yeah, it looks like we might have
Anybody
a question.
Else oh, do we?
You can always see when somebody's typing in Slack, so.
Oh, that's how you knew.
Well, we see. It's sometimes they may decide not to ask, so.
Yeah, sometimes it doesn't happen, right?
Right.
Ashley, you're like question coming in, and then it doesn't, right? Yeah.
You make them too nervous sometimes.
Very cool. Well, I do hope that everybody is enjoying Transform. I do advertise it within my school as being one of the really great conferences to be involved in. Or is it an unconference? Knowing Matt and all, I'm going to assume it's an unconference, unsessions and so forth, right?
So I'm not seeing
not
any.
A standard technical conference.
I'm not seeing any further questions, just a lot of thank yous now on the Slack channel. So I'll say thank you, Michael, for an awesome tutorial. Your interactive IPY widgets are wicked cool and way better than what I learned in Patrol. So thanks to everybody for watching. There's a whole lot more left in Transform. This has just been the first day of tutorials. There's a whole other set of tutorials tomorrow. If you like what you see here, please like and subscribe, especially to Software Underground, to our YouTube channel. And yeah, have a great rest of your Monday. Thank you all.
Thank you, everyone.